Okay, here we go. The law of the lever. Law of lever? Law of lever. I don't know. Um, so we studied the idea of torque last time, and torque just being the product of force and distance, and it's basically a rotational power, a rotational force. And if you look in this situation, I found this on the internet, and I thought that looked like Mr. Restall. So, but you know, if you look at a lever and you want to do work, right? You can lift this mass. So a lever gives us mechanical advantage because you can lift a mass by using a smaller force depending on where you apply it, right? So if he pulls back far enough, and this was Archimedes, right? Give me a lever long enough and I can lift the world. This is pretty much what we're saying. If we could make this thing long enough and we had the world on there, you know, not really, but kind of, right? Okay, so that's how we get mechanical, what's called mechanical advantage, and we're going to study mechanical advantage more in the next video. But you know, we want to get mechanical advantage out of a lever, and you can do that by putting less force in if you have a longer distance here. Okay, so first looking at just maybe this is maybe the key thing. If Mr. Restall's effort torque for product of force and distance, his effort is just a little bit greater than the load torque, which is that force, which is gravity times the distance to the fulcrum, then he can actually lift that thing, right? If they're exactly the same, it stays in what's called static equilibrium. But if he puts a little bit more in, so usually we talk about calculating what we call for static equilibrium, which is just staying put, right? And then the idea being that if you want to actually move a mass using a lever, whatever the static equilibrium force you need to apply, you put in a little bit more than that. Okay, so by static equilibrium, static is not moving, equilibrium it's happy, it's in a good spot. Okay, and for that to be true, then you just need your effort torque to equal your load torque. And if you want to move something, you make your effort torque just a little bit bigger than your load torque. So just as far as a couple definitions and like symbols, so you know what I'm talking about, so we can do calculations. Of course, that's what it's all about. So if I take this first class lever here, and there's my fulcrum, what we call they always call it arm. I don't know why, but it's really just a distance. The distance from the load to the fulcrum is called the load arm, okay? And so I call it D with a little L. So when you see like the formula, D with little l means it's a distance from the load to the fulcrum. DE would be effort distance, fulcrum to effort, sorry. And then load force is in a lever, it's almost always just the mass of the object times 9.8. Okay, it's the force of gravity. And then effort force is what a force you have to apply to get the thing. You know, if you're talking about static equilibrium, it's to either stay put or just like that tiny bit extra will actually make it move. And like I say, generally when we do calculations, it's about static equilibrium. It's about balancing them, and then sort of if you're designing something, the idea would you would know just your force have to be somewhat greater than that. So usually you calculate for the static equilibrium. Talked about this briefly, these three different types of levers, and there's a little lab that's pretty easy to do with the levers, okay? And you make each type because, I don't know, how could you memorize that? I wouldn't memorize that. I can't memorize it. Like first class is easy, it's a teeter-totter. Second class, you've got the load in the middle, and a third class, you've got the effort in the middle. And so, you know, really basic levers you're going to make up a fulcrum, get your own fulcrum in the classroom, use a meter stick is the lever itself, and you can put a mass as a load, and you can measure the force that you apply using the spring scales. So you'll be doing static equilibrium of levers, of the three different classes of levers. And it gives you an idea better how they work, and you could think about applications. I think we talked about that in an earlier video, like in your body, how there's different types of levers. So this law of the lever, the title of the note, law of lever, is for static equilibrium to happen, load and effort torque must be equal. That's all. And so if you want to do work, you want to make something move, you need just a little bit more effort, torque. So this leads to the formulas, okay? To make that true, torque is just force times distance. So the effort torque would be the effort force times the effort distance, or effort arm, equals the load force times the distance to the fulcrum from the load. And remember that in pretty much every case I can think of, the load force is just equal to mass of the load times gravity, because we're always talking about lifting something. Okay. So that becomes this formula here. And of course, depending on the question or the situation, you generally will be solving for one of these four things. Okay? Maybe you'd solve for maximum mass as well, in which case you'd call that MLG right there. So just a little example. You got two dudes on the teeter-totter, okay, big dude, little dude. And obviously they can't balance this thing. There's no way. However, if a little dude could move, move further away from the fulcrum, maybe he could. Okay, and so the way to figure out, so is where should the little guy sit in order to balance this? And more likely with this teeter-totter, because the poor little guy would have to move off here, which there's no more teeter-totter. Generally, you might make that work by having this dude move in closer, but it's not the way I worked out the question. So the things that we know then, we know the mass of the big dude, the little dude. Looks to me like the little dude will be almost twice as far away, right? Because he's about half the mass. But if we go through, let's call the big guys the load and the little guy the effort. I mean, that's not totally clear in this question, which is effort, which is load, so you can make whichever you want. So in this case, the effort force will just be, because all he's doing is applying his mass, so it'll be his mass times the 9.8. So there's his effort force. The load force will be the MLG, which goes in here. So we can sort of plug this into the formula to find out how far he needs to go. Oops, do you see my typo? That should be an DE. Change that to an E. Can I change it to an E? I can't. You can change it to an E. Anyways, works out to be 2 meters away, which is, like I say, because he's about half the mass, he's going to be about twice as far away. Right? He's 1 meter, he'll have to be 2 meters. And because of the design of this teeter-totter, that can't be. What really the question should have read is, where should this guy? He's going to have to come in towards the fulcrum, and so he's got to end up around 50 centimeters, right? Because he's, again, he's around twice the mass. So to keep the effort torque and load torque equal, he'd have to be half the distance. That'd be a better question. Another one, another first-class lever. So this man here is lifting a stone with a lever. So say it's a 300 kilogram stone, it's 50 centimeters away from the fulcrum. If we know that the most effort he can apply, which is basically his weight, right, his force of gravity, would be 1,000 newtons. So say he's 100 kilograms. 100 kilograms works out to about 1,000 newtons. How far from the fulcrum does he need to apply that force in order to lift the 300 kilogram stone? So same question. So this time we're solving for DE, right? So we're given the mass of the load is 300 kilograms. We know it's 50 centimeters away from the fulcrum, and we know that the maximum force he can apply is 1,000 newtons. So we're just going to solve for how far away he needs to apply it. Okay, so that's I think that's it for law of the lever. So there's that nice little lab you can do and some questions, and yep, that's it. This is almost the end of the unit. One big note is the last thing of the unit. Good for you. Good for me. We're done.